So for main group elements, the valence electrons are those in the outermost principal energy level. So the highest principal number, n equals 4 or something. In the hotel, these electrons are the ones on the highest floor. Okay. The group number is going to tell us how many valence electrons the main group elements have. So these are the 1A, 2A, 3A group numbers, right? The black ones up there. So if I look at nitrogen, nitrogen is in group 5A. Nitrogen has 5 valence electrons. If I look at fluorine, fluorine's in group 7A, 7 valence electrons. If I look at selenium, selenium's in group 6A. How many valence electrons? 6. Okay? So the valence electrons are really important because those are the ones on the outside. They're furthest from the nucleus. They're on the outside. And those are the ones that are going to interact with the electrons of other atoms. So the number of valence electrons is a big factor in how atoms behave, both chemically and physically. So, here we have group 1, main group elements, they have 1 valence electron. 3A has 3. 5A has 5, right? This explains the patterns that Mendeleev saw. The reason that he put helium and neon and argon in the same column because they had similar properties is because they have the same number of valence electrons. But wait, helium only has 2. Yeah, helium only has 2. But helium's first floor is full. It can't have 8 like these other guys. So hydrogen and helium are like the baby brothers of this element family, and they break a lot of the rules. And we just have to make allowances for them because they're small and they're cute, right? So helium has 2 valence electrons, but he acts like one of the noble gases that have 8 valence electrons. He's got 2 because he's just not big enough to handle 8. Okay, write an electron configuration for phosphorus, identify the valence electrons, and core electrons. Okay, I forgot to mention the core electrons. They're back here. So we have the valence electrons. Those are in the highest level or the highest floor of the hotel. The core electrons are the other electrons. So all the ones in the lower levels or the lower floors. So write an electron configuration for phosphorus, identify the valence electrons and core electrons. I'm going to do an orbital diagram first because I think we maybe still need pictures. So phosphorus, how many electrons? 15, right? So phosphorus, I don't know what that is. Phosphorus, come on, equals 15 electrons. So I'm going to draw our little hotel rooms here with their beds. So that's the first floor, the S room. Second floor, we've got an S room and a P room. Third floor, we've got an S room and a P room. There's also a D room, but I know we're not going to need that one, so I didn't draw it. Okay. So we're going to put the electrons in their beds, right? Right side up first, and then upside down. But when we get to P rooms, they're going to take their own beds because they can, right? So here we go. We've got 1, 2, 3, 4, 5, 6, 7. Now they have to pair up. 8, 9, 10, 11, 12, 13, 14, 15. We've got all the electrons in there. How many unpaired electrons does this one have? 3. There are 3 electrons that have their own beds. The previous example, we were supposed to say how many unpaired electrons there were, and I forgot. There weren't any. They were all paired up. Okay, So that part is not necessary, but it's helpful. So let's write the electron configuration out. So in the 1s room, how many electrons? 2. So 1s, 2. And in the 2s room, 2. And how many electrons in the 2p room? 6. How about 3s? 2. And 3p? 3. That's an electron configuration. Okay? It's faster than drawing boxes and arrows. I like the boxes and arrows though. So, we got the electron configuration. Now it wants valence and core electrons. So the valence electrons are going to be in the highest principal energy level. So we would recognize that because it's the largest big number, right? These are the principal quantum numbers, 1, 2, 2, 3, 3. These guys are in the 3rd level. This is the highest level that has electrons in it, right? In the hotel, it's the highest floor that has electrons staying there. So tornadoes, right? There was a tornado that actually did some damage in LA this week. I grew up in the Midwest where tornadoes were a really serious thing. They would decimate towns. I mean, just unbelievable. But so I bring the tornado to the hotel for the valence electrons because the tornado's going to come by. Oh, it caught it before it hit the floor. The tornado's going to come by and it's going to take off the top floors of the hotel. Tornadoes can do that. They can do some really strange things. They can leave part of it perfectly and take another part. So they can just take levels off. So what electrons are in danger in this hotel from a tornado? It's the ones on the top floor. Okay, so those are the valence electrons. So the valence electrons will be on the highest floor of the hotel. So the 3rd floor has 2 rooms that have people in them, electrons. And so it's everybody on that 3rd floor. Sometimes there's like 1 electron in the S room, and it's just that guy. Other times you might have, S and P, but it's not that there's 2, it's the highest floor.
If we wanted to, could we write it as NE and then the 3S2 and 3P3? Like the NE in the brackets?
Oh,
since that's last.
yes, the noble gas configuration? Yeah, we could. So if we wanted to do the noble gas configuration, we'd find phosphorus on the periodic table. So it's there in row 3. And we're going to go up 1 row to the far right end. That's the next smallest noble gas, right? So that's neon. And so we put neon in brackets. Neon has this electron configuration. And so to write the configuration for phosphorus using this shorthand, we're going to say, okay, the electron configuration of neon plus this. So that's also phosphorus. Yeah.
So because we know phosphorus is in 5A, instead of doing all that, can we just say, well, phosphorus is in 5A, so it has 5 valences?
Yeah. Yep, you can do that. This one is it just asks us to write the electron configuration, so we did that. But if it just says how many valence electrons, it would be 5. And if it asks you how many core electrons, we'll take the total number of electrons, subtract the valence electrons, and the rest are core. Yep.
What if we went to 4s? Would 4s be the valence
Yes.
electrons?
Yep. So if we kept adding electrons and we got electrons now staying on the 4th floor, yeah, those would be the valence electrons and these would not be valence electrons anymore. It's just going to take off the top floor that has people in it. How does it know? I don't know, but it does. Darn tornadoes. Okay, so how can we do this off the periodic table? So we can divide up the periodic table into 4 blocks of elements that represent the filling of the 4 quantum sublevels, the rooms in the hotel, S, P, D, and F. The group number is going to tell us the number of valence electrons. the row number, or the period, is going to tell us what the highest principal quantum number is for that element. That's the level of the valence electrons. It's going to tell us what's the highest floor in the hotel that's occupied right now. Okay, so these first two columns represent the S block. And how many electrons fit in an S room? 2. Oh, this is 2 columns wide. Why is helium over there? Because he's cute and he wants to be, and we let him. But really, he kind of belongs over here, right? Helium should be over there. The pink one, okay, so this represents the P rooms. How many electrons fit in a P room? 6, because there's 3 beds, right? 1, 2, 3, 4, 5, 6. The yellow is the D room. D room has 5 beds. How many electrons? 10. Guess what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F room, 7 beds. How many electrons? 14. Do I need to count them? There's 14. What? Isn't that crazy? Quantum mechanics was not a thing when the periodic table was put together. Mendeleev was just looking at patterns that he could observe, and he set it up like this. And then quantum mechanics comes along later, and they weren't trying to fit it to the periodic table, but it matched up. And that's just like kind of spooky, isn't it? So let's look at phosphorus again. So we find phosphorus here. It's in group 5A. We know it has 5 valence electrons. And those 5 valence electrons are in the 3rd row. They're on the 3rd floor, the 3rd principal energy level. And so that's going to be 3s2, represented by these 2 guys. And 1, 2, 3, 3 into the P room. Argon has more. It has 4, 5, 6. It has the P room full over here. Okay, so this periodic table is showing you the valence electron configurations for these different guys. And you'll notice that these guys all have the same type of configuration here. All that's changing is the floor number or the principal quantum number. So let's say we're writing an electron configuration for chlorine. So the noble gas configuration is the easiest. So here's chlorine. We're going to go up a row to the end, and we've got neon. And then after neon, we're just going to read this off the periodic table. So we've already taken into account those guys. And now we're going to go over here. This is 3. This is the 3rd floor of the hotel, the 3rd principal energy level. 1, 2. So 3s, 2. We got those guys filled up. And we go over here. This represents 3p. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3p5. It's kind of like a grid, like playing Battleship or something, right? So the second, over here, this is in P, so this is 2P1, 2P2, 2P3, 2P4, etc. Any questions?
What are we doing it for F?
We'll get to F in a minute.
Okay.
Yeah, D and F are kind of weird. We're going to do this P and S first. So, everybody okay with S and P? Determine the electron configuration of bismuth. Okay, so that is going to get into the D and F. So I think maybe I forgot something over here. So let's go back to this one. So these are the main groups, right? These parts that stick up. And so here the group number matches with the level. These are the transition metals. And if we look at this, doesn't it kind of look like it should be up there instead? Kind of. That would be, following a pattern better. I think of this as being like the San Joaquin Valley floor, which is sinking. Did you know that? We're pumping water out of the aquifers, and the floor of the valley is actually sinking very slowly, but it's measurable. So here, they pumped out too much groundwater, and it sunk, right? So these are the d orbitals, but they're not 4D. They should have been up here. And so for these guys, it's whatever period you're in minus 1. So these are in period 4, it's 3. This is 3, 4, 5, and 6. And then these guys are actually supposed to be wedged in here, which is actually what we have on the wall. That's how the periodic table's supposed to look. It doesn't fit on a piece of paper very well, though. And we don't use these guys very much because they're really weird and uncommon. And so they cut them out and just stuck them at the bottom. So if you need them, they're there, but otherwise they don't mess up the rest of the table. So these guys are sunk even further. And so here, those guys are going to be n minus 2. So these are the regular ones. They stick up, they match the numbers. This one fell down a level. This is n minus 1. This fell down another level. See, there's 2 levels here. That's n minus 2. So then this guy belongs in here, right? There's a gap in the numbers, right? 57, 57, 72. I don't count like that. 57, 58, 59, all the way through these guys. 71, and then 72. So that's row 6, period 6. So these are 6 minus 2, or 4F. 7 is this guy down here. 7 minus 2 is 5, so those are 5F. Okay? Now we can look at this other one. So bismuth. We're going to find on the periodic table, which can be a challenge in and of itself. There it is right there. So what's the previous noble gas? Xenon, right? Right here. So that's the previous noble gas. And so we can start with that. So it's the electron configuration of neon plus, so we go to this next row, and this is row 6, and the first 2 are the S group. So 6s2, 6s2. And then this is a D, but then it jumps down into here, right? So these guys are going to be, we're just going to do full electron configuration so we can practice. So chlorine, first thing is we have to find chlorine. Chlorine's over here. So I'm going to start at the top, and this is 1s. So there's 1s. Does that show up? Kind of. 2. 1s2. And then I come down here. See that? That's 2s. 2s2. Okay, I'm just going to draw lines through it because. And then over here, what's this? This is the which block? S, P, D, or F?
P.
That's P. And what level is it in?
2.
2. So this is 2P, and there's 6 in there. So 2P, 6. And then I'm coming over here, right? So that's 3S, 2. And then I skip across here, and I've got 1, 2, 3, 4, 5. That's 3p, 5. You see how it works? Oops, didn't want to do that. So the next one is silicon. So that one's right there. So again, I'm going to start at the top. I've got 1s2. This is 2s2, 2p6, 3s2, and then I'm only 2 into the 3p. So 3p is the next one, and there's only 2 in there. Okay, strontium. Strontium is down here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and this is where we need to be a little careful, right? Because this D is not the 4D. Because remember, the third floor had 3 rooms on it, the S, the P, and the D. Why is the 3D coming now after the 4S? Because it's more expensive than the 4S. It's further from the elevator. Anyway, this is 3D, right? So that's 3D. We're going to go all the way across that. Whoops. And so that's 10. And then over here, this is back to the regular numbering. So that's 4p, and we'll put 6 in there. And then we come down here, and that's 5s, and there's 2. So, this is the kind of periodic table. I mean, you're not going to have the colors, these colors, but those don't really help doing this anyway. All of that information about the levels is here in the periodic table. Right? It's going to take a little practice. Let's do oxygen. Oxygen is right up here. So oxygen is going to end, this is the second row, right? This is the 2p. This represents the 2p room in the hotel, and it's got 1, 2, 3, 4 electrons staying in it. That's going to be the end of its electron configuration. It's going to start with 1s2, 2s2, 2p6. And so, you can just count as you go along. 1s2, 2s2, 2p4, right? 1, 2, 3, 4. There's other ways that people have made to help the staggering of those levels. There's one where you write things out and you draw diagonal lines and stuff, and if you like that, go ahead, but I find it confusing when it's actually all right here. Any questions? We'll take a little practice. So that's all nice, right? And then there's the irregular ones. There's got to be exceptions to every nice rule. So that sublevel splitting causes the 4s to be lower in energy than the 3d, but it's not a very big difference. And so there's some irregularities when you're filling those. Sometimes they don't fill 4s first and then 3d. And this is when you get into the transition metals. And these are things that you don't predict from the periodic table. They've been determined experimentally, and you just have to remember them. I'm only going to require you to remember 2 of them. So these are some of the irregular ones. Chromium, copper, molybdenum, ruthenium, and palladium. And I just want you to know the first 2. So let's draw out the last part there. So this is 4s, and then we've got 3d. So for chromium, it's got 6 electrons there after argon, and so we would expect it to go 1, 2, 3, 4, 5, 6. Right? That's the pattern we learned. Well, Groupon got involved. So there's a Groupon-coupon that if you have the S room and the D room both half full, you get a discount. It's always weird things like that, isn't it? So here what's happening is this guy is going to move up here. You can see why he'd want to do that, right? Gets his own bed. And isn't that more symmetrical? Nature does like symmetry. This configuration is a little bit lower in energy than this one. So, because the difference in cost between these rooms, the difference in energy between these levels is really small, and so that little Groupon deal, if the guy moves up here, this actually lowers the energy a little bit for everybody. So we get 4s1, 3d5. So I could give you, on an exam, what's the electron configuration for chromium, and I would expect you to give me this. Of course, is that going to cause you to fail the class? Absolutely not. Let's look at copper. So copper has a total of 11 electrons here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's what the rules tell us, right? There's another Groupon deal. Look, this one's almost full. Wouldn't it be nice if that one was full, and then this one would be kind of nice because it'd be half full, right? So that's what happens. This one moves up here.
Have irregular electron configuration?
It's not only these 5. These are the 5 that the book mentions, and I think only the first 2 are worth space in your brains. Now, if you have a homework question that asks you for one of these other ones, and you do it the regular way and it says, it's wrong, you can look in the book, and it does tell you these other guys.